In this third part, I want to discuss selected case studies. Okay, we start with temperatures. Temperatures in Australia, temperature extremes in Australia. Because if you studied what I just told you, you actually understand graphs like the one that I show you on the next slide. Okay, this is a temperature distribution in Australia, okay, for early January 2013. It's not expressed in terms of temperature values, but it's expressed in terms of temperature percentiles. Okay? So these colors shown here correspond to percentiles. Okay? And the temperatures commonly way above 40 degrees on this day. Okay? However, what do these percentiles mean? You learned it. The 100% here, percentile means, well, that's the hottest ever recorded temperatures. Okay, think about these distributions that you get. The one in a 1,000 events corresponds to the 99 percentile. 99%, and have a look at that. So you get these very extreme heat waves over most of South Australia and Victoria and Tasmania, and extremely hot in parts of Tasmania and near Whyalla on the Eyre Peninsula in this area. Okay. So from this alone, you can see that this is an extremely rare case of an extremely warm condition in Australia. Okay, so now you want to learn how these heat events, atmospheric heat events, has the number increased in Australia? How do you work that out? And this is shown on the next graph. So let's have a look. Atmospheric heat waves in Australia. So this is a graph, okay, and this is from the latest State of the Climate report from 2022 from the Bureau of Meteorology for Australia, and it shows you a graph, and let's have a look what's shown here. The x-axis shows you the year. It starts in 2010 and then goes to 2020. And the y-axis shows you the number of days Australian mean temperatures were in the warmest 1% of records. Okay, which shown here. You can see it increases. You can see it. So just hang on a little bit, because I try to explain it. So what they did. They used daily data. Okay? They sorted all data according to the values. Yeah? The lowest temperatures on the left and the warmest instances on the right, and the highest temperatures on the right. Okay. So based on the entire records that they have. Okay. And then they only looked at 1% of the record, and I only grabbed the 1% of the warmest, without even knowing the years or the dates. Okay? And then they counted the number of days for each year contained in the record. Okay, so this is shown here. For example, let's take an example here for 2020. Yes, you had a total number of 40 days. Okay, which the warmest ever recorded temperatures in Australia. So that's how you can produce these very nice time series, which are actually without the use of any threshold value. Just sorting temperature data, looking at the warmest 1% of data and counting. Again, you can see the sharp increase of the number of heat wave days in Australia. Okay, not in every day, so you get some years when it is lower, and lower, but you get overall a sharp increase. So that's a nice method, okay, to analyze heat wave data, temperature data. So now another example. Okay, and this is for China, for Eastern China, looking at changes in the mean temperature and the number of heat wave days. Okay. So this is done. Here shown are the number of summer season heat wave days and mean temperature anomalies relative to the 1955 to 1984 average. Okay, this is shown here. It's an anomaly, the mean temperature relative to a reference value. Okay, and this temperature anomaly in this graph is shown on the right, and it ranges between, there's the 0, 2 degrees plus, and minus 1 degree, minus 1 degrees. So you have the mean temperature, and you can see there is a little change, some fluctuations, and then you get an increase. Since 1990, you get that increase. Okay. The red curve shows you the heat wave days, the number of heat wave days, and that's based on a maximum, on a temperature exceeding 35 degrees Celsius. Again, you can see that in the 1960s and 70s, you had instances where you had 4 days or 5 days of, heat days, heat wave days or so, but then you had a decrease. But more recently, since the 1990s, you have a trend, a positive trend, an increase in the number of heat wave days. Okay. And on the right side, we show this shows a correlation. You plot one against the other. The temperature anomaly is plotted against the number of heat wave days, and you can see that there's a correspondence. Okay, you have an increase in the temperature anomaly and coinciding with an increase in the number of heat wave days. So what it tells you is that the warming in Eastern China that you get is actually relates to an increase in the number of heat waves. Okay, and that's a concerning message, because you have, because the warming could come through other means, like the nights could become warmer, or it could be a seasonal shift. But here, a key feature is that actually the warming plays a big role. Okay, these heat waves play a big role in the warming signal. All right, I don't want to interpret too much. I want to show you some examples of how you can actually analyze extreme events, okay, based on one-day data and just counting. That's what you essentially do here in these examples. And then you can count, and you do worldwide, and you can put all the data together, and you can produce graphs like this. Okay. Again, I don't want to interpret too much. I just want to warn you with graphs like this, because this one is a so-called stacked plot. Okay, it does not show you the curves for each parameter on its own. It starts with one parameter. So let's see what's shown here. So the number of events of droughts is the blue one. Okay, but then the next one is added on top. Extreme temperatures are added on top, and then the floods are added on top. Okay, and so on. And you have to be careful with the interpretation. Just because the entire curve shows an increase doesn't mean that the blue curve, which actually talks about wildfires here, actually also experiences an increase. Okay? This is misleading, because the sharp increase in one parameter leads to a bias of everything which is added on top. Like the green one here. In this example is floods. In this example, you can see that there is a sharp increase in the number of floods, but it influences the entire graph above it. So be careful with the interpretation of stacked plots. Okay, I want to show you the better way to discuss changes in extreme events is firstly you produce graphs for each type of extreme events separate. Okay? And the second principle here is, I don't know the second principle. Anyway, so that's what's done here. It's from publication. Here's the linked reference. So what they did is they looked at events and per decade, and then they compared all the different decades. For example, for extreme temperatures, based on a threshold value, okay, and then number of extreme events per year, and then shown as a change over the years, and you can see that there's an increase. Okay, and you can compare different continents: Europe, America, Africa, Asia. Yeah, you can compare, and you can see the increase. You can compare different regions. Droughts is another example here. Okay, for droughts, for example, and you can see number of events per year. Africa has the biggest number, but the interpretation becomes more complex, because if you just look at the data from 1980, you can see it's a decrease, increase, decrease. Well, it's hard to tell, predict into the future from that. Okay, there are storm is another example. Storm is another example, which is, you can do this, you can plot these numbers, but in order to understand changes, you have to know a little bit more about the cause and the effect relationships that you actually have. Floods is the other example shown here for floods, and you can see an increase, but then followed by a decrease. The general problem that we have with the interpretation of these is that you actually don't have that many data points. Here, essentially, you have 1, 2, 3, 4, 5, 6, 7 data points, and now you want to conclude anything from it. Okay. However, you can see some changes. Okay. So this is something that we have to look out for in the future. As we gather more and more data. Okay. All right. So I want to show you one other example, and this is the last example that I want to show you. It's about tropical cyclones. Okay. And again, it's about counting. And so all that's done here, there are examples of counts of hurricanes. This on the left. This one talks only about the Atlantic Basin storm count. So we're in the Atlantic Ocean, in the warm water. It includes subtropical cyclones, a little bit further away from the equator, and you get named storms, hurricanes, major hurricanes in this list. Okay, and now you're asked to interpret what's happening. And this is tricky, isn't it? It's relatively tricky. It starts, relatively early here. So we're around 1910, 1920. That is an increase. There seems to be even more recently an increase in the number of cyclones. Okay, but you have to be careful with the named ones. Because the named ones, there might be just more that have been named. You have to study which criteria were used. Okay, but anyway, another example here. Tropical cyclones from 1970 to 2017 which have occurred in the Australian region. Okay? Severe are the red ones, not severe are the yellow ones. If you look at that, it looks like a downward trend going down the curve, so you get less. But tricky for the severe ones, again, you had a period of where you had more severe, seems to be less severe. Okay? So it's very, very tricky to tell, to interpret, but the actual exercise of counting and putting these graphs together is not a very tricky one. Okay, it's actually, it's based again on numbers and plotting numbers as a time series. Okay, so and this now concludes the third part of this lecture.